Welcome to the deep dive. Today we're venturing back into that fascinating world of integer sequences.
Good place to be.
It really is. And, our guide, as always, is the Online Encyclopedia of Integer Sequences, the OEIS.
An indispensable tool, really. We should also mention it thrives thanks to the OEIS Foundation and its donors.
Absolutely. Huge credit to them. So the sequence we're diving into today is A0000221.
Right. Often called the happy numbers orbit of 5.
Exactly. So the core idea, how does it work? What's the rule?
Well, it's based on a simple iterative process. You start with a number.
Okay, in this case, 5.
Precisely. You take its digits. Well, 5 only has one digit, square them, and sum the results.
So 5 squared is just 25. That's the next term.
Correct. Now you repeat the process with 25.
All right, so digits are 2 and 5. 2 squared is 4. 5 squared is 25.
Add them together.
4 plus 25 gives us 29.
Perfect. Keep going.
Okay, 29. 2 squared is 4. 9 squared is 81. Sum is 85. Then 85. 8 squared, 64. 5 squared is 25. Add them. 89.
And from 89?
Let's see. 8 squared, 64. 9 squared, 81. That's 145.
Okay.
Now 145. Digits 1, 4, 5. So 1 squared is 1. 4 squared is 16. 5 squared is 25.
Summing those up.
1 plus 16 plus 25, that's 42.
Okay.
42 gives us 4 squared, 16 plus 2 squared, 4, which is 20.
Getting simpler numbers now.
Yeah. 20 gives 2 squared, 4 plus 0 squared, 0 squared, so just 4. Then 4 squared is 16.
Right.
16 gives 1 squared, 1 plus 6 squared, 36. That's 37.
Nearly there.
37 gives 3 squared, 9 plus 7 squared, 49. 58.
I'm friendly, 58.
5 squared, 25. 8 squared is 64. Add them. 25 plus 64 is 89.
Ah, there it is.
We're back to 89. Wow.
Exactly. You've hit the cycle. So the sequence goes 5, 25, 29, 85, 89. Then it enters this loop.
Right. The loop is 89, 145, 42, 24, 16, 37, 58.
Yeah.
And then back to 89.
That's the one, a cycle of length 8. It just repeats indefinitely from that point. It's quite neat how it settles down like that.
It really is. And the OEIS entry points out some interesting things here, too.
Oh, yeah.
Like, M.F. Hasler noted this sequence, A0000221, is basically the same as A00079, starting from the 5th term.
Interesting. So they converge after a few steps. That suggests a shared underlying dynamic kicking in.
Yeah, and it also mentions this is the orbit of 5 under the map A0003132.
Which is the function we've been using the sum of the squares of the digits. Naming the function itself helps clarify things.
Right. And Hasler also suggested, apparently, that maybe the sequence could even start at index 0.
That's often a point of discussion with sequences. Where do you consider the start? But focusing on A0003132 really frames it nicely. It's one example of applying this function repeatedly.
You could start with any number, really.
Absolutely. And see where it leads. Some might hit 1 per Duanov list.
Yeah.
Those are the actual happy numbers. Others, like our number 5, fall into cycles.
It's cool how the OEIS entry includes code, too. Like, there's Mathematica code.
Nestless, probably.
Yeah, Nestless Plus at integer digits, #2 and 550. It generates it directly.
Shows the power of functional programming for this kind of iteration.
And it mentions padwrite to show the repetition visually. Plus, there are snippets for PRI, Magma.
And Haskell, I saw that. Iterates A0003132 very concise.
It really highlights how different tools can tackle the same mathematical concept.
And how computation lets us explore these things so easily now. You can generate thousands of terms in seconds and really see the patterns emerge.
For listeners who want to dig deeper, there are references mentioned too.
Ah, yes, like Hansberger's Ingenuity in Mathematics. Classic.
And one by Arthur Porges in the American Mathematical Monthly called A Set of 8 Numbers.
That title seems pretty relevant, doesn't it? Given the cycle length we found, he likely analyzed this specific cycle.
Seems likely. There's also a link to a table by Vincenzo Librandi with the first 100 terms.
Useful for checking work or just browsing the values? These resources show this isn't just a new curiosity. People have looked into these patterns before.
And finally, the keywords. Non, base, easy, nice.
Which sums it up well, I think. Non-negative integers.
Tied to base 10 digits.
Conceptually easy to grasp.
And, well, nice. It has a certain elegance.
It does. It's a great example for students starting out in number theory. Accessible, but leads to interesting behavior.
So, to kind of wrap up our look at A0000221, we followed the number 5 as it went through this process of summing the squares of its digits.
And we saw it wasn't happy in the sense of reaching 1, but it found its own kind of stability.
Right, landing in that repeating cycle of length 8, 89, 145, 42, 24, 16, 37, 58.
It's a fascinating glimpse into iterated functions and the kind of order that can emerge from simple rules.
Definitely. This whole deep dive just from one sequence, it really shows the depth there. And maybe it leaves a question for you listening, especially if you're studying number theory.
Mm-hmm.
What is it about this specific function, summing the squares of digit, that causes these cycles? Why cycles and not, say, infinite growth or chaos for all starting points?
That's a great question. Are there properties, the starting numbers themselves, that might predict maybe the length of the cycle they fall into or if they reach one?
Yeah, can you look at a number and have some intuition about its fate under this iteration? Something to think about.